Good afternoon, everyone. Today I'm going to present our work, GLEAR, a graph logic enhanced RAG framework for legal question answering. As we know, LLMs are quite good at understanding and generating legal text. However, when it comes to real-world legal question answering, we often lack structured reasoning and explicit legal grounding. This is partly because legal knowledge is actually highly structured. For example, legal articles and case descriptions are inherently connected, but existing methods don't make good use of this structure. And also, they often struggle to clearly explain what legal provisions or similar cases they rely on. So overall, the answers generated by LLMs are not professional or reliable enough in real legal scenarios. This is a problem that our work aims to address. Then I'll briefly talk about why standard RAG is not enough. Because standard RAG basically splits knowledge into chunks of text and retrieves them. It's essentially still text matching. It doesn't consider the relationships between pieces of knowledge, like how cases is linked to a legal article. Also, the retrieved information is fragmented, and it doesn't form a complete reasoning chain. So in this work, we try to address this problem by introducing a graph-based framework that can better capture logical relationships between legal knowledge. We propose GLEAR, which integrates knowledge graphs with retrieval augment generation to improve both reasoning quality and answer reliability. We construct a heterogeneous legal knowledge graph where cases, articles, and historical queries are connected through relation edges. Then on this graph, instead of simply retrieving text, we first retrieve relevant nodes and then search for reasoning paths in the graph. This serves as a reasoning chain from the query to relevant legal knowledge. Finally, we use these paths as additional context to guide the LLM to generate more reliable answers. Next, first I'll introduce how we construct this complete legal knowledge graph. First, we define three core types of entity nodes: legal articles, cases, and historical user queries. Legal articles mainly come from four major law codes, like the criminal law, civil code, etc. Case descriptions come from public legal datasets, and user queries are based on real legal questions. And we also use DeepSeek for some data augmentation. Between these nodes, we construct file type of relationships like article to case to represent the connection between different types of legal knowledge. To give a key example, for case-to-case relationships, we compute similarity between two cases using both semantic similarity and overlap of legal elements. If the similarity exceeds a threshold, we add an edge in the graph, and the similarity is also used as a edge weight. The two figures on the right, the top figure is a local snapshot of the knowledge graph, and the bottom one shows a global view. We use Neo4j for visualization. Later during inference, we rely on this complete graph to retrieve relevant nodes and optimal reasoning paths. Next is the logical enhanced inference stage, which consists of these three steps. The first step is knowledge retrieval. We adopt a drill-driven approach. On one hand, we use vector similarity for semantic retrieval, and on the other hand, we use BM25 for textual matching. Then we combine the scores and select the top three most relevant entity nodes. The second step is based on these nodes, searching for the highest weight logical paths in the knowledge graph. These pieces of knowledge form a reasoning chain, and I'll explain this algorithm in more detail next. The third step is to convert the paths into natural language and use them as additional context input to the LM, get it to generate more reliable answers. Here, let me explain the optimal path search strategy. First, we take the top k returned entities in the previous step and consider all paths as start and end nodes to construct candidate paths. Then, during path search, we use a greedy strategy. At each step, we select the edge with the highest weight, that is the strongest connection, and expand the path step by step to maximize the overall path weight. The weights can come from similarities like case-to-case edges, and for edges without predefined weights, we assign a default value of 1. So the path starts from query-related nodes and goes through relevant legal articles and similar cases. Finally, from our candidate paths, we select the top and optimal path as the basis for reasoning. The figure on the right is a simple illustration. Here are our experimental results in terms of performance and efficiency. First, from the table on the left, we can see that GLEAR achieves significant improvements across 5 legal tasks, such as chart prediction and present term prediction, with an average improvement about 40%. We also compare it with standard RIDE, and it's clear that GLEAR performs better. This shows that introducing graph structures and logical paths is indeed more effective than simply retrieving text. The on the right, the time complexity graph shows that although GLEAR is slightly slower than the base model, its growth curve is flatter than native RIDE. This means that as the number of query increases, GLEAR is more efficient and stable. So overall, GLEAR outperforms existing methods in both performance and efficiency. Next, the final part of results shows our framework performance on free-form legal question authoring. We constructed 300 random legal questions and evaluated the responses along these dimensions: accuracy, professionalism, and comprehensiveness. As we can see, compared to the base model and RIDE, our method achieves clear improvements across all 3 metrics. Another important point is that from the score distribution in the figure, GLEAR not only has higher average scores, but also significantly fewer low score cases. This indicates that its outputs are more stable. Finally, to briefly summarize our work, the core idea of our method is to combine knowledge graphs with RIDE and further introduce explicit logical path reasoning so that the model can reason along a clear legal logic. From the experimental results, whether on traditional legal and natural tasks or free-form Q&A scenarios, our method improves model performance. At the same time, by leveraging graph structures and logical paths, it also offers certain efficiency advantages. Finally, we'd like to acknowledge the support from the National Natural Science Foundation of China and related projects. That's all for my presentation, and thank you for your attention.